Hello Master 8303 students, let's begin lesson 2, real numbers. Here in lesson 2, we're going to study some basic properties of real numbers, classified into 3 categories. First, the arithmetic properties. The properties of real numbers associated to the arithmetic operations, addition, subtraction, multiplication, and division. That's section 1. And then the order property. The properties of real numbers related to the inequalities, greater than or less than. That's section 2 of this notebook. And then in section 3, we cover the geometric property. By the way, in lesson 2, we are not going to try to define the real numbers or define the algebraic operations or things like those. And we're going to do those way later in the second half of the course. For now, let us assume the existence of real numbers and the existence of well-defined addition and multiplication, and then assume they satisfy these basic properties, which we call the field properties, by the way. And then, based upon these, we can define the subtraction and division as inverse operations. Alright, so much for the arithmetic properties. That was easy, right? Not so fast. We are dealing with the foundation, so let's pay close attention to what it means by well-defined. This is an important concept. We cannot just define anything. After making appropriate definition, unless it is really obvious, we have to prove whether that definition makes sense or not. Addition is well defined. What do you mean by that? Well, please recall addition is a binary operation, so it's a double variable function. Let's suppose a is that function, a for addition, and more traditional function notation like this. Yes, you can define it as summation. And is it a well-defined function? Basically, we're asking these properties. So anything from the domain must be matched to something in the target. Domain and target. And this gives rise to the first property that R is closed under the addition. Alright? Closed under the addition. So it's part of being well defined. But here's bigger fish. I mean, in order to have a well-defined function, what's the most important aspect? Yeah, domain and range, that's important too, but much more important aspect is the same element in the domain must give rise to the same element in the range. So if x1, x2 are the same, y1, y2 are the same, or in the pair expression, x1 and y1, that pair is, and x2, y2, that pair is the same, then end result must be the same as well. Here's an example. Fraction expression, 2/3 plus 1/3 is 3/3. And the decimal expression, 0.666 and so on, plus 0.3333 and so on, add up to 0.9999 and so on. They mean the same thing. Just different expressions of the same real numbers. See those? That's just an example. But in the end, what do you get from these two? Close under the addition, and then the equality is preserved when we add the same real number to both left-hand side and right-hand side. You see, y1 and y2 are the same, right? Adding these two. In a special case, I can simply add y1 and then y1 there as well. So I can add the same real number to both left-hand side and right-hand side of the equality. Actually, that is not a property of equality. That is actually property of addition. Excuse me, it's not really a property either. It's come from and whether addition is well defined or not. In any case, yeah, well, okay, we have been using the term, the property of the equality for so many years, so let's stick to that. But in any case, that's what we just covered. Addition is well defined. Likewise, you can do the same thing to the multiplication. Yeah, you can express multiplication as traditional function form, applies to pair notation, if you will. In any case, that's what we mean. Close under the multiplication, yeah, domain and target, yes. And also, if you multiply the same thing to both left-hand side and right-hand side of the equality, equality is preserved. Same thing, same idea. All right, well defined. We just went through that, and that was extremely important concept, and they can be tricky. How tricky? Well, let's work on some of those. Let's see. I know for a fact that everybody went through this multiple times for, I don't know, God knows how many years. So everybody is totally comfortable with all those, but let's scrutinize a little bit. Associativity, that means we can regroup. Okay, that's what it means, all right. Commutativity, we can change the order. All right, that's what it means. Identity, that means zero. Well, here's a problem. Can we define zero? Such a real number exists, all right. That's one of the properties given. But then again, what if there are so many of them, like infinite many of them, so that this expression is meaningless? Of course, that is not true. Can we prove it? In other words, is zero well defined? Similar thing here. Inverse property. Given x, what if there are so many y's with same property like this? Infinite many y's such that. That's, of course, doesn't happen. We have to prove that there is one and only one y with this property for given x, so that we can define it as negative x. Is it well defined? We have to establish that. Similarly for multiplicative identity or the unity and multiplicative inverse or reciprocal. And then after that, finally, we have well-defined subtraction and division, because now negative y, the additive inverse of y, is unique, so we can define subtraction like this uniquely. So now it's well defined. Same goes for the division. 1 over y, the multiplicative inverse or reciprocal, is unique for given y, so we can define the division like this. So all these are well defined, provided that we prove that additive identity is unique, additive inverse is unique, and so on. How do you prove these? Well, let's see, let's go back. What do you mean by additive identity? Well, that's a property, isn't it? Okay, all right. Using this property, we're going to set up like this. 0, 1 and 0, 2 satisfy all those, and then we want to prove that these two are the same. So our aim is to fill up this dot, dot, dot. How do you do that? Stop the playback and try. Did you get it? Actually, it's pretty easy. It's that easy. Why? Because 0, 2 is an additive identity, this one, which I'm highlighting in red. So adding the additive identity doesn't change anything, so this equality is preserved. O1 stays at O1. This red. This equality, red equality, is true because O2, which I highlighted in red, is an additive identity. Likewise, please note that this O1 is additive identity. So adding additive identity doesn't change anything. Therefore, we have this equality, which I'm now highlighting in blue. So red is giving red equality, and blue is giving blue equality. That completes the proof. Well, for a little bit more complete proof, you can actually open up my answer key here. So basically that's what we want to prove. O1 and O2 are the same, provided that they are both satisfying the same properties. And yeah, the same thing. Now, can you set up something similar to additive inverse? Try that. Stop the playback and try that. Got it? So basically that's what you want to do. Suppose that y1 and y2 are both additive inverses of x, then y1 and y2 are the same. How do you prove that? y1 is equal to y1 plus 0. Why did I get 0 involved? Because we are talking about additive inverse. So something adding up to 0. So starting with 0 is a good idea. And y1 is y1 plus 0 because 0 is an additive identity. And then remember, 0, we're talking about additive inverse of x. So we can express this 0 as x plus y2. Why y2? Because y1 is already there. Now once we have that, it's going to be easy from this point on. I can always regroup y1 plus x plus y2 thanks to the associativity. So we have 0 plus y2, and that's y2, and that's what we wanted all along, right? y1 and y2 are the same. If both y1 and y2 are additive inverses of x, consequently the additive inverse is unique, therefore we can define it as native x. By the way, here's a bit more precise proof. Yeah, the same thing here, but here's even more precise version. So what did I do here? At each step, I wrote why that holds. And each explanation here is almost trivial, but we have explanation here, and I know that, but it's so trivial that I'm skipping. That's one thing. And I'm doing this computation, but I'm not exactly sure, so I'm skipping the explanation. That's very different. You see, you should be able to do this every time somebody requires you to. That completes the proof. And of course, these are quite tedious, so most of the time you skip, and that's okay. But you gotta know the reason behind each equality. So when you teach students, at least for first several weeks, I think it's a good idea to force students to write down write down those explanations. At least I went through that kind of training myself too. I thought it was stupid, but well, over the years, I think it was good introduction to proof. At least I felt that way. Well, okay, all right. So much for first two problems. How about the other two problems? I'll leave those to you. Something similar about multiplicative identity or unity, multiplicative inverse, reciprocal. They are different names of the same thing. Okay, so much for 1.2, and in the next video let's discuss 1.3 and other things from this section.